So this is Chapter 9, the last chapter in General Chemistry 1411, which that's pretty nice. This chapter is all about molecular geometry, so the shapes of molecules, and bonding theories. And so we'll look at like MO theory and valence bond theory. So the first thing we want to talk about is molecular shapes. Molecules aren't two-dimensional shapes. So like the way that we draw, for example, methane, CH4, it would appear as though there would be a 90-degree angle between any of these bonds, and that all of the atoms would lie in the same plane. But that's not what methane looks like. It looks much different than that. And so we'll find that the 3D structure of methane shows that the angles come out to about 109.5 degrees. And it looks something like this. So we have a carbon atom in the middle and the 4 hydrogen atoms on the perimeter. And if we were to measure the angle, it would be very close to 109.5 degrees. All right. We refer to this shape as a tetrahedral geometry. So we call that a tetrahedral geometry. Tetrahedral shows up quite a bit in chemistry. So we want to look at the concept of electron domains. And if we can predict what shape the molecule is going to be, provided that we have drawn the Lewis structure correctly. So if we have a valid Lewis structure, then figuring out the shape is pretty straightforward. We need to be able to count the number of electron domains. This is a really, really easy thing to do. For example, and the way that you do it is you just find around a particular central atom either a single bond, or so here's a single bond on methane, or a double bond counts as a domain. That counts as one domain. A triple bond also counts as one domain. And a lone pair of electrons can also count as one domain. So if we count the number of domains around each of these central atoms, we can determine what the electron domain geometry is going to be. So let's start by looking at the carbon. Well, clearly there are 4 domains around that, so we'll put a 4 next to it. This carbon has 3 domains. There's the double bond, and then each of the single bonds counts as a domain, so that's 3 domains there. This carbon has 2 domains. There's a single bond and a triple bond, so there's 2 domains around that carbon. And this nitrogen has 3 bonds and 1 lone pair, and since the lone pair can count as a domain, that's going to give us a total of 4 domains. So let's go to problem 9.1 on the in-class assignment. So here is 9.1, and it says give the number of electron domains around the central atom for each of these. Now I've drawn the Lewis structure on this, and I did that for convenience purposes. But I did not put lone pair electrons on perimeter atoms because that just made it look more confusing. I only put lone pair electrons on the central atom. So in case you're wondering, yes, there should be lone pair electrons on like chlorine and fluorine there and the oxygens over here, but I decided not to do that. So let's count the number of domains. This is not very hard. Here on beryllium, there are 2 domains. On this boron, there are 3 domains. Here on sulfur dioxide, we've got a double bond, and a lone pair of electrons. This, by the way, is a hypervalent version of this. I think either we saw or we drew one where we had a single bond on one side and a double bond on the other, kind of like with ozone. But on this one, we can draw 2 double bonds. Anyway, there's 3 domains there, so a double, and a lone pair. On the carbon here, we've got 4 domains. We saw that one on the overhead. This one also has 4 domains. Oxygen here on the water has 4 domains, 2 lone pairs, 2 single bonds. All right. Scroll down here a little bit, and we'll get to this phosphorus. Clearly, there are 5 domains there. This sulfur also has 5 domains. This bromine also has 5 domains. And then here, xenon, we've got 2 bonds, and 2 single bonds and 3 lone pairs, so that's 5 domains there. This sulfur has 6 domains. This iodine also has 6 domains. Xenon here has 6 domains. And then this one, I'm not going to write one on this because there's no central atom. We've only got 2 atoms there, so there's no central atom. And then here on this carbon, there are 4 domains. So 4 domains. Now, we're going to be using those for something else. So I'll set that aside, and we'll go back to our in-class presentation. Okay, so now we want to look at the concept that's called valence shell electron pair repulsion model. So the valence shell electron pair repulsion model is quite simple. Sometimes people will call it VSEPR. So the VSEPR model, it says this: the best arrangement of a given number of electron domains is the one that minimizes repulsions among them. In other words, we try to get those domains as far apart from each other. Domains are made up of electrons, and electrons like to repel each other. So we'll find that once we know the number of electron domains, then that number of electron domains will dictate the electron domain geometry. So in fact here we've got, when we have 2 domains around the central atom, we'll find that the best arrangement is a 180-degree angle between the 2 domains, and and so there's 2 domains there, and so there we go, there's the 2 domains, and we call that linear, which makes sense. If it's 180 degrees, they're all in a straight line. When we have 3 domains, we will find that they will all be in a plane. So there's no need to make it a 3-dimensional object. It'll all be in a single plane. And that the angle there will come out to 120 degrees. Well, if they're all the same, it'll come out to 120. And we refer to that as trigonal planar. So that one is trigonal planar. On this one, when there are 4, we already used this word a bit ago, is the word tetrahedral. So with 4 domains, they will arrange themselves 109.5 degrees from each other, and they will be tetrahedral. And that's 4 domains. With 5 domains, there's no way to arrange the domains so that all of the angles are equal. So we'll find that there are 2 angles, and the 2 angles are 120 degrees and 90 degrees. And we will refer to this as trigonal bipyramidal. So trigonal bipyramidal. All right, that's 5 domains. And with 6 domains, we will be able to get everything having the same angle. We'll get 90-degree angles between everything, and we refer to that as octahedral. So now that we know that, we're going to go back and answer the problem. So just as a real quick note, what I want you to memorize is I want you to memorize those electron domain geometry names: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. I also want you to know that once you know the number of domains, you can immediately figure out what the electron domain geometry is. And then finally, the other thing I want you to remember are those angles. So let's go look at number 2 on the assignment. And number 2 is using these same things, and it's just give the electron domain geometry for each of the central atoms in the table above. So it's pretty straightforward. Again, once you know the number, you know the name of the electron domain geometry. I'm going to write the electron domain geometry name in red, and then I'll use a different color for the other stuff. So we'll do linear for that because there's 2. With 3, it is trigonal planar. All right, so trigonal planar. Here, this one's 3, so it's also trigonal planar. All right. With 4, that will be tetrahedral. All right, this one has 4, so it is also tetrahedral. And then this one has 4, that is also tetrahedral. Okay, when we have 5 domains, with 5 domains, it will be trigonal bipyramidal. So trigonal bipyramidal. This one has 5 domains, as does this one, so these are also trigonal bipyramidal. All right, and then this one is also trigonal. Okay. Look, this one also has 5 domains, so it's also trigonal bipyramidal. With 6 domains, it will be octahedral. This one also has 6 domains, so it is octahedral. And this one has 6 domains, so it is octahedral. All right, this one doesn't have a central atom, so we're going to skip that. And then this one has 4 domains, so it is tetrahedral. All right, and then we'll do molecular geometry next. So let's switch back. All right, so here we've got molecular geometries. So molecular geometries. So molecular geometries are the arrangements of only the atoms around the central atom, not the lone pairs. However, we have to know where the lone pairs are because the lone pairs will dictate which molecular geometry you have. So if you don't know how many lone pairs are on the central atom, you're not going to be able to figure out what the molecular geometry is, at least not very easily. All right, so with each electron domain, there might be more than one molecular geometry. It is possible to have more than one molecular geometry. In order to determine the molecular geometry, your step should always be 1, get a valid Lewis structure. If you have a valid Lewis structure, then your chances of getting the correct molecular geometry are going to go way, way up. If you have a bad Lewis structure, your chances of getting the wrong answer is going to go way, way up. Okay, so get a good Lewis structure. Next, you'll determine the electron domain geometry. You do that by counting the number of domains and then applying which geometry is applicable. Okay? And then finally, you use the number of bonding domains and non-bonding domains to determine which molecular geometry it is. So look at the total number of domains to get the electron domain geometry, but then we look specifically at the number of bonding domains and non-bonding domains to get the molecular geometry. So we'll start with the linear electron domain geometry. This is where we have 2 domains. Okay, when we have 2 domains, there's only going to be one molecular geometry, and that one molecular geometry will be linear. And if you have a lone pair, then you're only going to have 2 atoms. And so if you only have 2 atoms in a molecule, then your molecular geometry is going to end up being linear no matter what your electron domain geometry is, because 2 points make a line, so it has to be linear. So if you've got 2 electron domains and they are both bonding domains and there are no lone pairs, then the name of the molecular geometry is also linear. All right, so the name of the molecular geometry is also linear. So I'm just going to go back over here, and just as an example, you'll see So this one, there's two bonding domains. There's no lone pairs. So the name of the molecular geometry, which is the next question, is also linear. Okay, so it's also linear. One thing that's kind of useful to remember is if you have no non-bonding domains, in other words, no lone pairs on the central atom, then your molecular geometry is going to have the same name as your electron domain geometry. So again, if you have no lone pairs on the central atom, then your molecular geometry will have the same name as the electron domain geometry. So within the trigonal planar electron domain geometry, there are two molecular geometries that we will find. There's trigonal planar. Again, it has its same name if all three domains are bonding domains, and I like to refer to it as the number here. So so this is 3, 0. So 3 bonding domains, no lone pairs on the central atom, and that's going to be also trigonal planar. If you've got 2 bonding domains and 1 non-bonding domain, so 2, 1, then you're going to have the arrangement that is called bent. Oh. And I meant to, while we were doing this, I meant to come back over here. I meant to show you some of the molecular models that we have. So I'm going to raise my camera a little bit here. All right. And so for the BeCl2, these are the models that I normally would pass around class. So here is BeCl2. So there's beryllium in the middle, and we've got the 2 chlorides on the perimeter. And you can see that they are 180 degrees apart from each other. That one's not very exciting. So this one is also linear. For this one, we've got BF3. And so here is BF3. So the boron is in the middle, and the fluorines are on the perimeter. And then you'll see that they are all in the same plane. That's why we call it planar. So all 4 of those atoms are in the same plane. And we would see that the angles come out to 120. So the molecular geometry, because this one is 3, 0, the molecular geometry has the same name as the electron domain geometry. And we'll call that trigonal planar as well. So that is that one. All right, and then one that is bent. Here I've got the sulfur dioxide. So our sulfur atom is in the middle. We've got 2 bonding domains and 1 lone pair. You'll see I represent the lone pair just by a little sphere there, a little thing that sticks out from the atom. So that lone pair pushes on these bonds just like the bonds push on each other. So there, that one is sulfur dioxide. So that one we will call bent. So that is the molecular geometry for that one. All right, within the tetrahedral electron domain geometry, there are 3 molecular geometries. All right, so 3 molecular geometries. One is tetrahedral. This is where all 4 of them are bonding domains, and we have no lone pairs on the central atom. We've got trigonal pyramidal. That's where we've got 3 bonding domains and 1 lone pair. Ammonia is an example of that. And then we have bent. And this is where we have 2 bonding domains and 2 non-bonding domains. And so 2, 2, that one is going to have the name bent as well. So let's go over and look at CH4. So here's CH4. Again, there's 4 bonding domains around this, and there's no lone pairs on that central atom. So no lone pairs on the central atom. With no lone pairs, it's going to have the same name as its electron domain geometry, and we will call it tetrahedral as well. When we've got 1 lone pair, The name that we had for it was trigonal pyramidal. The reason we call this trigonal pyramidal, you'll see that all three of the hydrogen atoms are in a plane, but the nitrogen atom is outside of that plane. And it's a little bit difficult to see with this camera angle, but the nitrogen is above the plane of my table here. So, so the electron domain geometry is tetrahedral, but the angle is called trigonal pyramidal. So there is the trigonal pyramidal. Okay, and then for water, this one, not very surprising here. This one is bent. There's our water molecule. So the oxygen, the hydrogens are at approximately 109.5. We'll find that angle's a little bit different here in a minute. I'll show you that. They are the lone pairs, but that one is bent. So that one is bent. Okay, so let's go back. So now for non-bonding pairs and bond angle. For non-bonding pairs, we're going to find that non-bonding pairs, like the lone pairs that we saw on the ammonia and on water, that they are larger and they sit closer to the nucleus than the bonding pairs. So they just spread out a little bit more and they sit closer to the nucleus than the bonding pairs. And as a consequence, we'll find that the angles between the actual bonds are compressed a little bit. So our typical angle for a tetrahedral is 109.5. However, for ammonia with that one lone pair, the one lone pair that's on top, that lone pair pushes harder on the bonds than the bonds push on each other, and it compresses the angles between those bonds down to 107. About 107. For water, the angle gets compressed a little bit more, and it goes all the way down to 104.5. Okay. Well, in addition to that, we'll also see that double bonds and multiple bonds will affect bond angles. So double and triple bonds have they're larger electron domains. They've got more electron density. There's more electrons than the single bonds, and as a consequence, we'll find that they push a little bit harder on the single bonds than the single bonds push on each other. So there's a greater repulsive force between the double and the single than there is between the two singles. And as a consequence, you'll see here on phosgene, which is a nasty chemical, by the way, on phosgene, that the angle here, 124.3, is larger than the expected 120-degree angle that we would see in a typical molecule, and that the angle between the two single bonds comes out to only 111.4. All right, so there we go. So trigonal bipyramidal electron domain geometry. So this is a case where we have an expanded octet. We have more than 8 electrons around the central atom. And we'll find that there's really no way to arrange these so that all of the angles are equal. And as a consequence, we end up having two distinct positions on a trigonal bipyramidal electron domain geometry. And that is, we have the axial position and the equatorial position. So the axial position and the equatorial position. All right. And again, I'm going to show the model of phosphorus pentachloride here. And you'll see as you look down this that, these two are 180 degrees apart from each other. If you look here, the angle between this bond and this bond comes out to 90 degrees. But if we turn it so that we're looking down the long way, the angle between those two bonds comes out to 120 degrees. So we've got a larger angle in between these. The ones that are, there's 120 between them, we refer to those as equatorial, and that the ones that are opposite each other, we refer to those as axial. So you could kind of imagine it spinning on its axis. and that these are along the equator. All right, so now we want to look at the trigonal bipyramidal molecular geometries that go with it. There are 4 molecular geometries here. With these 4 molecular geometries, so within the trigonal bipyramidal electron domain geometry, the 4 molecular geometries, well, the first one is where it keeps its name, and that's where we've got all of them as bonding domains, and we don't have any lone pairs. When we do get lone pairs, those lone pairs curiously end up on the equatorial position. It just so happens that you get fewer repulsions if you put it in the equatorial position than if you put it in the axial position. All right, and so that we refer to as seesaw. So that's where we have 4 bonding domains and 1 lone pair. And I'm going to go over and show you that structure real quick. So here is that structure for sulfur tetrafluoride. And you'll see there's 4 bonding domains and 1 lone pair. So that's going to give us 5 domains. Well, this is what it looks like. So again, here, this is an axial position. There's an axial position. They're exactly 180 degrees apart. If we look down that axis, we see the 120-degree angle between our equatorial positions. One of our lone pairs is at an equatorial position. And if you rest it on the tabletop, you'll see that it kind of looks like a seesaw, right? It kind of goes back and forth. So it kind of looks like a seesaw. And so that's why we give it the name seesaw. All right. So that's 4-1. If we've got 3 bonding domains and 2 non-bonding domains, we're going to refer to that as T-shaped. Again, we will find that that the lone pairs end up in the equatorial position. All right, so here is BRF3, and I've got that BRF3 right there. So there is BRF3, and there's the bromine. There are the 3 fluorines, and these 2 are in axial positions. This one is in an equatorial position, and you'll see it looks like the letter T. And then if you look down the axial positions, you'll see these 2 lone pairs are in equatorial positions. And that's why we get the letter T. So that is T-shaped. And then finally, our 4th molecular geometry here is linear. And it just so happens if you replace 3 of the domains with lone pairs, you will get the 2 remaining bonding domains will be in the axial position, and it will give you a linear molecule. And so here I want to show you what that looks like. So here is the linear molecule XEF2, which is actually on the next page here. And so there's our xenon, there are the fluorines, and all of our lone pairs are in the equatorial position. So that one is the xenon difluoride. Okay, so now that I've shown you those, let's go ahead and jot these down real quick. Here, this one, 50, that one is it's also trigonal bipyramidal. All right, this one, 4-1, that one is seesaw. This one, the 3-2, is T-shaped. And then here, this one, the xenon difluoride, this one is linear. That one is linear. All right, we're going to look at that here in just a second. All right, so now we're going to look at the octahedral electron domain geometry. We'll find that there are 3 molecular geometries. Not surprising, if there are no lone pairs, the first one's going to have the same name. So octahedral, if all 6 domains are bonding domains, then that is the octahedral. And I'll show you what that one looks like. So here is sulfur hexafluoride, and you'll see that the angles between any two adjacent ones always comes out to 90 degrees no matter which direction you look at it. So that is our sulfur hexafluoride. So sulfur hexafluoride, pretty cool there. All right, so that's that one. You may remember the sulfur hexafluoride during the chapter on gases. I talked about sulfur hexafluoride. You remember I showed you a little video with two cute little girls, and they breathed in the sulfur hexafluoride, and it made their voice really deep. And that's because the sulfur hexafluoride has a really high molar mass, and the molecules move slower. Well, that's a reminder. That's what that was sulfur hexafluoride. All right. If we've got 5 bonding domains and 1 lone pair, we're going to call that one square pyramidal, and I'll show you why. So here is IF6, or IF5 rather. There's IF5, and when we look at this, you'll see that there's the 5 domains. These 4 are all in the plane of this atom, more or less, and that this one is kind of like at the top of a pyramid. So you can kind of imagine, and I just can't pull my camera back too far, but you can kind of imagine it looks like a square-shaped pyramid. So that's why we call that one square pyramidal. So that one is square pyramidal. And then going back over here, our situation where we have 4, 2. If we have 4 bonding domains and 2 non-bonding domains, 2 lone pairs, we will refer to that as square planar. And we're going to do number 3, and we've actually already done most of number 3, but we'll finish it up here. So here is xenon difluoride. You'll notice that the 2 lone pairs are exactly opposite each other. That puts all 5 of the atoms, the xenon and the 4 fluorines, all in the same plane. And so that's why we call it planar, and because it's kind of a square shape, we call it square planar. All right, so now that we've gone through all of those, let's go ahead and finish this up. So this one is also octahedral, all right, because it's 6, 0. All right, this one is 5, 1, so it is square pyramidal. All right, this one is 4, 2. 4, 2 we will find is square planar. All right, we can do a molecular geometry for this because you remember back if there's 2 atoms, the molecular geometry is always linear. So this one, it does have a linear geometry, but I mean that's sort of obvious because 2 atoms have to be in a line. So all right, and then here we've got 4. They're all bonding domains, so this one is also called tetrahedral. All right, so we've done the electron domain geometry, and we've also done the molecular geometry, and we need to predict if things are polar. So we'll go back and look at that. By the way, if we've got larger molecules, those larger molecules can possibly have more than one electron domain geometry or molecular geometry in the same molecule. So it is possible for them to have more than one geometry. This is the molecule of acetic acid. So there's a CH3, COOH, and this is, we'll find that this one has 4 domains, so it is tetrahedral. This one that's the electron domain geometry, and all of them are bonding domains, so that means it's also the molecular geometry. On this carbon right here, there are 3 domains. They're all bonding domains, so that means the electron domain geometry is trigonal planar, and the molecular geometry is trigonal planar. Here on oxygen, we've got 2 bonds, and there are 2 lone pairs. The lone pairs aren't shown here, but 2, 2, that gives us a bent molecular geometry. Here we can go over here because it's talking about it here. It's a bent molecular geometry and a tetrahedral electron domain geometry. So tetrahedral, remember, it takes into account the lone pairs as for its shape. All right, so we now want to look at how shape and polarity are related. So I'm going to give you a set of rules that you can use to determine if something is polar. So the polarity of a molecule is going to depend on both the polarities of the individual bonds and the geometry of the molecule. So to determine if a molecular compound is polar, you can just go through the following questions in order, and you need to do these in order. If you don't do them in order, then things get a little ugly. But if you do these in order, you should be okay. And the first question is, just check, are there any polar bonds? If there are no polar bonds, you don't need to really go any further. Your molecule is going to be nonpolar. So we just look and see if there are any polar bonds. And if there are no polar bonds, then our molecule is nonpolar. But if there are polar bonds, we need to ask more questions. Next, are there only two atoms in the molecule? All right. And so if there is a polar bond and there's only two atoms in the molecule, then the molecule is polar. If there are more than two atoms, then we need to move on to the next question. So this one is just sort of to catch those two atom molecules. Our third question is, are all of the electron domain bonding domains, are all of the electron domains bonding domains, and are all of the atoms identical? So if all of them are bonding domains and they're all identical, then that means that yes, the molecule is then the molecule is going to be nonpolar. And just as a couple of examples of that, and there are many, but a couple of examples of that that I have here. Here I've got the PCl5. With PCl5, we'll find that these two dipoles cancel each other out and these cancel each other out. So even though there are polar bonds in this molecule, overall the molecule is not polar. This one, all of the things on the outside are the same, and they are and there are no lone pairs. There are no lone pairs. I left the room there for a second. So our fourth question is, are all of the electron domains bonding domains, and are there different atoms attached to the central atom? And if this is the case, then the molecule is usually polar unless the dipoles happen to cancel each other out. Now, they usually don't, but some weird stuff can happen. So I always throw that caveat in there. Usually it's going to be polar, but sometimes things will cancel out. All right, at this point, we should have taken care of all the possibilities for things that have all bonding domains, and we should be left only with molecules that have lone pairs. So at this point, you should have a lone pair on the central atom. If you don't have a lone pair on the central atom, you need to go back and make sure that your question you didn't get the answer on one of those previous four. So if we have a lone pair, are there different atoms on the central atom? And if yes, then the molecule is polar unless the dipoles cancel each other out. So again, that's sort of we can kind of go back to that previous thing about dipoles canceling out. We'll look at a picture of that here in just a moment. And then finally is if all of the atoms are the same on the perimeter and there are lone pairs, is the molecule in the 2,3 or the 4,2 category? And if yes, then the molecule is nonpolar. Let me show you why I picked those two. The 2,3, that is xenon difluoride. So here is xenon difluoride. We've got two bonding domains and three lone pairs. That's why I call it 2,3. And we'll also see that the two bonding domains are exactly 180 degrees apart from each other. So there's a dipole here and a dipole here, but those dipoles cancel each other out. So this ends up being nonpolar. The other one is 4,2, and here we've got the 4,2 With 4,2, again, we do have polar bonds. These two are polar, and these two are polar, but these two cancel each other out, and these two cancel each other out. And then the lone pairs make sure that everything stays in the same plane. But most of the other molecules that have lone pairs will end up being polar. So let's look at a couple of these situations, and I have a printout sheet, and you can look at this. All right, so I have the calculator printout sheet, not the calculator, but the printout sheet determining if a molecule is compound is polar or nonpolar. So you can refer to this while you're working on these and learning these. You won't be able to use this on the test, but you can at least have these instructions while you're learning it. So if we look at the carbon dioxide molecule that is right here, and says, are there polar bonds in the molecule? Yes, then we're going to move on. Are there only two atoms? No, there's more than two atoms. Are all the electron domains bonding domains, and are all the atoms identical? Yes. So we do have two bonding domains, and there's no non-bonding domains. There's no lone pairs on that central atom. As a consequence, we'll find that this molecule is nonpolar. So again, this is number 3. I encourage you to print out that page so that you can look at that while you're going through it. So if no, then we'll move on to question 4. All right. Well, we already took care of that. Let's look at water. Water. All right. Are there any polar bonds? Are there any polar bonds in the water molecule? Well, yes. Okay. Are there only two atoms? No, there's 3 atoms, so we can move on. Are all the electron domains bonding domains? No, we have lone pairs. Are all the, no, they're not all bonding domains, so 4, we're going to move on. At this point, you should have a lone pair on the central atom. We do. Are there different atoms? No. All right. Is the molecule the 2,3 or the 4,2? No, this one is 2,2, so therefore, no, this is a polar molecule. So we'll find that this is polar. Now, why is it polar? The reason that it's polar is that these two dipoles don't cancel each other out. And when they don't cancel each other out, we'll get a net dipole that is the sum of those two. The thing about dipoles is they kind of act like vectors. And when they act like vectors, they can add together with a direction. All right, here's one that is, there's no lone pairs and they're all the same, so that is nonpolar. Here, there's only 2 atoms and it's polar, so therefore it is, the molecule is polar. This is one, let's see, on number 4 where it says, are all the electron domains bonding domains? Yes. All right, so here, these are all bonding domains. And are there different atoms attached to the central atom? Well, yes. If yes, then the molecule is polar unless the dipoles cancel each other out. Well, you can see here that the dipoles won't cancel each other out because here we've got a dipole between carbon and chlorine, and there's nothing on the other side to cancel it out. So we'll end up having a polar molecule. All right. For ammonia here, we will end up with a polar molecule as well because we have a lone pair on the central atom. All right, and then finally here, this one is 4 bonding domains. They're all bonding domains, and there's no lone pairs. These are all the same, so that one is going to be polar. All right, I'm going to lower my camera here just for a second. Get that stuff out of the way. All right, we want to answer number 4. Number 4 down here says, predict whether the molecules in the table above are polar or nonpolar. So polar or nonpolar. All right, and we can get this sheet handy so we can refer to this. All right, are there any polar bonds? Yes, there are polar bonds. Beryllium, chlorine, that's a polar bond. And let's see, what else do we have? Are there only two atoms? No, there's more than two atoms. Are all the electron domains bonding domains, and are all of them identical? If yes, then the molecule is nonpolar. Well, this is nonpolar. The reason we know it's nonpolar, is because we have two dipoles and they are canceling each other out, kind of like we had in carbon dioxide in the presentation. All right, this one is also one where we've got, they're all the same, they're all bonding domains, and so this one is also nonpolar. All right. Here we've got a lone pair on this one, but it's not the 2,3 or the 4,2, so this one is going to be polar. All right, methane, we've got 4 bonds. So 4 bonds, 4 bonding domains, no lone pairs, so this one is going to be nonpolar. All right, this one has a lone pair. We do have polar bonds. It has a lone pair. It does not have, let's see, it does not cancel each other out, and so this one is going to end up being polar. And it's not the 2,3 or the 4,2. I'll show you the 2,3 and the 4,2 when we get to them. Water, well, water we know is polar. So water we know is polar. So we've got 2,2 here. That one is polar. We saw that one on the presentation. All right, we'll scroll down a little bit more here. So here we've got trigonal bipyramidal. You'll see that they've got 5 bonding domains. They're all the same. So that one's going to be nonpolar. There are no lone pairs. This one has a lone pair, and it's not 2,3 or 4,2. So this one is polar. This is the same. This is not 2,3 or 4,2. It's 3,2, not 2,3. So we don't want to confuse that. So this one is also polar. All right, we finally have reached the 2,3. As I mentioned, on the 2,3 here, these two dipoles are exactly opposite, so they cancel each other out. And so this one is nonpolar. All right, this one, they're all the same. There's no lone pair, so this one's also nonpolar. This one, we have a lone pair. It's not a 2,3 or a 4,2, so this one is going to be polar. All right, on this one, it's the 4,2. It's one we've been waiting for, so this one is nonpolar. All right. This one, if we go back, the second question, are there only 2 atoms in this polar bond? Well, yeah, there's only 2 atoms, and we know that bond is polar. So this is going to be a polar molecule. If you have one bond, and that's it, and it's a polar bond, then the molecule is polar. All right, and then this one, that chlorine, the carbon-chlorine bond is polar, and the carbon hydrogens don't cancel it out, so this is going to be polar. Okay, so I'm going to stop the video there, and we'll pick up with the next section on the second video.